Hey guys, welcome back to another video in the weekly paper series. This time we are going to discuss papers, but I also came across a nice article which I thought I might share because it is pretty cool and it goes into the details of what mixed precision does. So, what mixed precision is that um, the neural network is trained in FP16. Um, because it is more efficient, but it's mixed because certain weights are kept in FP32 while the gradients are stored in FP16. That's why it's mixed. It's not all FP32. The reason why we don't do all FP16 or all, so we do all FP32, but we don't do all FP16 is because it is numerically unstable. And the way to do mixed precision in PyTorch is that you just call this function or this context block autocast, and you specify the d type, and then you compute the loss. Now this is a black box because you kind of don't know what's going to happen or what is happening inside this, because this takes care of everything. So this article goes into the details of like what is happening. So I will just summarize this article, and I highly urge you to check this article out. So so in mixed precision, the model weights, activations, and gradients during the forward and backward pass are FP16. However, so this would be the ideal case if everything is FP16. However, just doing this causes gradient underflows. So this is not what mixed precision is. This is just if you do it in FP16, there would be issues. So this is a standard gradient update loop. So where you have your parameters, the gradient, you update the parameters, so everything is in D-type FP16. But now, if your gradients are smaller than 2 to the minus 24, it will underflow to 0 because note, FP32 has higher precision, so it can take lower values. However, those lower values will go to 0 because FP16 doesn't have enough resolution. So for very tiny values, the gradients would become 0. And this is kind of a problem. And this is where we get the numerical instability. So weak and mixed precision is a way of avoiding this. The reason why this is an issue, you would think is, so first of all, you would think like, why do we care about gradients so low? But let's take a look at what the distribution of gradients is. So this blue thing is the distribution of gradients, and you see a lot of gradients are quite small. If you remember, like the gradients, especially in the earlier layers, get multiplied by the gradients of later layers, so the values keep going down. So a lot of them are quite small, and if you go to FP16, this would just, around the minus 24 mark, they would all be clipped to 0, which is not good. The idea here is, can we just shift this distribution inside the FP16 values? And it's pretty simple. You just multiply it by a factor that shifts the distribution, and you need to ensure that you divide by the same factor so that you don't just scale everything. And that is this idea of loss scaling. And here, this gives an idea, like in code, the author explains, how loss scaling works, but the idea is just, you move the distribution inside the FP16 range, and then you get rid of the scaling factor. So that's one thing. The other thing is to keep, whenever you do parameter updates, make sure the parameter updates are always in FP32. So you store the parameters in FP32, you compute the gradients in FP16, and you add them to the 32-bit ones. So we use FP16 weights for a forward and backward pass, but at the optimizer step, we update the FP32 master weights. So here's a neat example, or the neat idea of what's going on. is, let's say, so here there are two layers, two linear layers rather, the weights and biases of the two linear layers, and in the forward pass we convert them into FP16. We do the forward pass, and in the backward pass, note that we converted back to FP32. So the backward pass, the update is on the full FP32 weight. So that's the idea. And the interesting thing here is, if a lot of operations require FP32 to work, so softmax on your CPU won't work on FP16 because there is no implementation of it. So you really need FP32 for softmax. However, CUDA has a way around it, because CUDA is highly optimized and they have kernels for FP16, because internally CUDA does so for example, in MATMUL, the multiplications are done in FP16 and the partial products are accumulated as FP32. So this is all part of the cuBLAS gem, which is the BLAS version of CUDA, the matrix multiplication libraries. So this is the CUDA details, but this is what is happening under the hood when you call that torch.autocast. And the reason why FP16 is so fast is not just because of the low precision is more performant, but that's due to the hardware. So NVIDIA GPUs have these in each of their SM units. A GPU is made of like a bunch of like thousands of SMs, I think. And so there are tensor cores, and tensor cores are dedicated to do FP16 computations, and they do them quite well. So that's why it is pretty good. So yeah, I'll post a link to this article below, but I thought that was pretty cool. So that's mixed precision. Now going back to the paper world, this kind of interesting paper came out, which is buffer of thoughts. So just like chain of thoughts and tree of thoughts, there is this buffer of thoughts, and the idea behind it is so for a given query, the chain of thought and few prompting techniques have certain manual prompts, and they can, some work good for some tasks, the other work good for the other tasks, but overall the accuracy is not so good. So can we and the same is for the tree of thoughts and other techniques, can we take a step further and cleverly decide what prompting technique should we use for a given problem at hand? So I think it's best explained with this diagram. Here's a problem, some math problem. If you applied this one hop chain of thought, it would have like not done so well. If you had done this multi-hop planning thing, again, not so good. But instead, if you have all these thought templates, like different ways of solving different problems, and we distill our problem and do like a RAG kind of thing, and we get the best thought that would be suitable for the task, and then do the reasoning step, that's what the author claimed gets the best results. So another paper in this whole thought-based, prompt-based reasoning, planning domain. That's all I had for this one. Moving on, finally, the other interesting paper that I wanted to talk to you about is this block transformer one, where they have a global and local transformer block that does, how should I say it, that does attention at a global and local level, and it can lead to faster inference. So note, like when you have large sequences, global modeling is hard because you attention matrices grow as n squared. Can we so this is another paper that tries to keep inference forefront, try to optimize for that. And the way they do it is you break your sequence in chunks, and each block will have an encoder. So here the chunk size is 4. So all these 4 get encoded into an embedding. And now, so this is called, let's say, the block embedding. So then now you have a block decoder in which you generate embedding based on just these block embeddings. So you do an attention just based on these block embeddings. So this is the block decoder. And then at a token level, you just inject all these blocks when you're doing the token decoding. So that way, the model, so this block contains all the context captured from the previous 2 blocks. Pretty straightforward idea. I feel like we've seen variations of this across the board. I guess in Transformer XL, there's kind of like the same idea, but yeah, but yeah, another paper about this similar kind of thing. So yeah, this is pretty much all the interesting things I found last week. Hopefully you like these, and we'll see more papers every week. Yeah, that's it for this video. I'll see you guys later.